Yeah, one of them. Okay. On a lot of dynamic programming today. Questions about anything? Really, separators that we discussed last time. Remember graph separator, don't forget them. The concept, yes sir?
I think the current due date for homework 6 is on Thanksgiving Day. Can we just kick it to the Sunday since we're not going to have class anyway?
Have I ever refused extension request? I did, but not frequently, sure. Yes. And I suggest that we'll have homework 7 probably because, I mean, it's one of these questions that I can never be happy with everybody. People that have 2 bad homeworks want homework 7. People that have only 1 bad homework don't want homework 7. But I cannot win it. But we are covering a lot of materials. And I'll go lighter. You know, like it's not that I'm oblivious that you have other courses and you have other deadlines and it's end of semester and etc. Okay, so I'm putting a lot of things under the umbrella of dynamic programming because in my view they are all fitting very nicely under this umbrella. We talked about hierarchical partitions of graphs. That was just one example in how do we use dynamic programming. If you remember, the big picture over there was if my graph has a property that I can split it with a small separator, like in planar graph, it's of size square root n when n is the size of v, then it makes a great algorithm because now when I need to compute the distance from S to T, or I need to have a data structure that allows me to answer quickly queries of the type, given 2 addresses, what is the shortest path? Either way, just as a single query or as a pre-processing and then a bunch of different queries, I can, instead of computing the big picture of from every address of Phoenix to every address in Tucson, pre-process the distance, which will need memory, ignoring running time, which will take memory of all addresses of Phoenix times all addresses of Tucson. Or I can just say, store two one-dimensional arrays that will be from every address in Phoenix, what is the distance to Picacho Peak and what is the distance to this jail city at the middle of I-60. So it's just one path to any one of them with the prices. The same goes when you have the addresses in Tucson. So far we are in two one-dimensional data structures from each one instead of one huge quadratic dimension, the n squared set. And now when I have to actually make a decision, how do I go from Tucson to Phoenix? Depending on the address, I'll check how much it costs me to go to the middle of I-60, how much it costs me to go to the middle of I-10, and compute it from the other direction and just ask what is the best one. That's just an example of how do I use small size separators that a lot of graphs exhibit. That there is a small size separator, set of vertices that if you remove them, you'll break the graph into 2 pieces. And hopefully each one of them has substantial size. Now, it doesn't make sense to just shave tiny sliver of the graph. I want a lot of vertices in each side, that's at least 2/3 n. The separator has a small size. Again, the examples that I suggest to keep in mind for separator will be a grid of square root n by square root n, and the separator is just one row in the middle. And when I'll compute distances from S to T, I'll compute the distances from S to each vertex in the separator. Similarly, from T to each vertex in the separator. The separator has small size. I'm going through it very fast because we discussed it. And now I can combine the 2 solutions. And I can solve each sub-problem separately or recursively find separators inside each sub-problem. And what I showed you in the little post is that actually if you're talking about road networks, then in road networks there are actually much smaller separators. If you're asking how many ways can I get into Tucson, you can isolate Tucson by cutting very few main roads, and you can isolate a neighborhood by, well, you'll not isolate it, but if you'll assume that everybody that comes to this neighborhood uses one of the highways, then there are just that many highways that enter the neighborhoods or a city or a state and so on. So the separators are actually of a very, very small size. Moving along. I want to show more examples of a plane separator, just to show you, polygon triangulation. A plan for today of how much we'll cover out of it would be to talk about a polygon triangulation. We'll talk about clustering of points. And we'll talk about DAGs and we'll talk first about Bellman-Ford. A lot of you know Bellman-Ford. I'll go through Bellman-Ford very quickly because it's a very short algorithm, and it's very easy to generalize it to many other problems, including the multi-commodity shortest path that somehow sits underneath it, and how we are using it in DAGs, how these two combines together. We are still all under the umbrella of the dynamic programming. And if we'll have time, we'll start talking about a greedy set cover. And I'll show you the bound due to Hoch bound that I found much stronger than the log n bound that you find in the CLRS. It's much more useful and much stronger. Okay, we'll cover whatever. Maybe it's a bit ambitious to hope that we'll do all of it today. Okay, let's talk about polygon triangulation. So polygon, you'll know what it is. There is a polygonal path that surrounds it. I'll assume that the polygon is simple. It looks like a fence, and inside the fence there is a region. What makes a polygon non-simple? That is a non-simple polygon. That is a non-simple polygon. None of these cases happens in this example. Okay, and this polygon represents some shape, maybe something that I scan with a 3D laser scanner, something that I want to tell my GPU to render, a laser 3D printer to print. Everything likes triangles. It's a very common and convenient primitive to work with. So I want to partition the polygon into small, meaningful regions, namely triangles. So how will I partition a polygon into triangles? I can add Steiner points that suggest somehow a further refinement. Steiner points is like, if I want to say, it's completely general trivia. If I want to say the way I want to represent this polygon, or to split this polygon into triangles, would be I'll add a vertex somewhere in the middle and partition it in this way. Maybe there is some advantage. And this is called a Steiner point. And there are good reasons why to consider Steiner points, but not in our class right now, where we're essentially using such polygons as an excuse to see a pretty elegant, clever dynamic problem. Okay, so now Steiner points. So let's define what is a chord. A chord in the polygon will be a segment which is fully inside the polygon. That would be a chord. And it starts from one vertex and ends in another vertex. And any triangulation that I'm willing to consider will be defined by such chords, again, segments, fully inside the polygon, which would be start at a vertex, ends at a vertex. My chords cannot start at the middle of the polygon edge, only start at vertices. And to create a triangulation of the polygons, I just find one chord and then find another chord with the limitation that I don't allow the second chord to cross the previous chords. Chords are not allowed to cross. You can add them between vertices, but they are not allowed to cross. So what happens when you're adding one chord is that you increase the number of triangles out there by one. So if I have an n-gon and I start adding chords, and I see at some point that I'm left with 4-gon. With 4-gon, it means there is yet one chord that you can add. Okay. Sometimes it's unique, sometimes I have a few options, but if it's 4-gon, then I can add this chord. And to create a triangulation, I'm just adding chords as long as I could without letting them to cross each other. Okay. Two chords, if they share the endpoint, that's absolutely fine. But crossing is not allowed. So, kind of easy to check how many triangles do I have when I triangulate a triangle. It was a cute sentence. Well, exactly the original triangle. If I triangulate a 4-gons, I'll have at the end 2 triangles, 5 gons, like in this case, 3 triangles, and in general, in any triangulation, you'll end up with n-2 triangles, and the number of chords that you will need for this process is n-3. Not very exciting, but just to know that the number of triangles will be the same, no matter what. Now, the algorithm that I'm going to show you will work on any simple polygon, convex or not, I don't care. So this algorithm that I'm going to show you will work with very small modification for this polygon that is not convex. I just have to be careful not to create a chord that will go outside the boundary. Okay, just these chords are not allowed. But to present this algorithm, let's assume that the polygon is convex. Again, it doesn't limit the algorithm one bit. It just said that I don't have to add checks of a chord is fully inside the polygon or not. At this point, everybody understands what is triangulation of a polygon? Everybody understand? Okay. A very legit question is, why am I teaching it in the chapter about dynamic programming? Well, because it shows a different type of dynamic programming that use the main principles that we are known for so far, which are what? What are the main component of dynamic programming that we saw in the 4 major examples so far, namely LCS, edit distance, Frechet, and dynamic time warping. We said we want to have a small number of sub-problems. I have a small number of sub-problems, each can be easily indexed. What do I mean when I talked about the LCS? I needed to tell you a subproblem is represented by a pair I and J, and it refers to find the LCS of a prefix of I characters of X, the prefix of J characters of Y. But that was the way that we indexed, or we gave name to all the subproblems. And what other principles of dynamic programming are we going to use is that the big problems use solution to smaller problems. Problems of the whole string use some of the solutions for some of the prefixes that we played with. The big problem, solution to the big problems is composed by solutions for sub-problems. That was quite important. And another important principle of dynamic time hopping was that once I solved a sub-problem, I can memorize, store somewhere the cost of the solution, and next I don't need to recursively solve it again. I can just look at the table and the cost of the solution is written there. And when I solve larger problem, I can use already computed solutions. What I had to be careful in all these algorithms was to make sure that when I'm solving a sub-problem and I need a solution to a smaller problem, it needs to be already computed. I need to access the problems. That was the importance of the loops for the I and J, where I had to make sure that all the smaller sub-problems are already accomplished. And we'll see that all these principles exhibit themselves, but now it will be, the way that I'm accessing the sub-problems will be different, and somehow surprising. What am I trying to optimize? Well, there is exponentially many triangulations of the same polygon. It's not hard to see. I'll give you a convex polygons. It's very easy to see that you can, even without creating the chords to intersect, there is exponentially many. So even though my search space is exponential, I want to give an efficient algorithm, polynomial. And I need, obviously, a cost function. And the cost function that I picked for this problem was, let's look at the areas of the triangles in my triangulation. And let's have as a cost function the sum of the area of the three triangles in the triangulation. The sum of the areas of in the triangulation, well, that doesn't tell me much about the quality of the triangulation, because in any triangulation, the sum of the areas is exactly the same. But it's just the area of the original polygon if I sum up the areas of all the triangles. So instead of summing the area of the triangulations, I got a closed monster here, and some people here. If anybody wants monster for the people, it's early in the morning. I'm sure that you have other deadlines. We can split it, maybe. Let's see if we can split it. Okay. I mean, how many? What? There are cups. Yes, I remember them. That's it. How many? How many wants monster? 0, 1, 2. Show me hands. None. Okay. We can. I think that up to 3 it's still effective. But good. So this cost function makes sense. I don't want to minimize the area, but I want to minimize the area's square. I take every triangle, compute its square, the area square, and sum it up. Why does it make sense? Because look at the numbers. Look at two numbers, 17 minus x, and another number x. And I'm looking at these equations, and of course it sums to the same thing. What I take from the first component, I'll add to the second component, and there is no pressure to any particular solution. But if I'll add the square over here, try to convince yourself that there is some fairness that is imposed when I'm adding the square, because at least unconstrained, my solution would be when these two numbers are equal to each other. That's when I'll reach the minimum. If I get to if x equals 0, then it's just 17 squared plus 0 squared. So of course, as large as I can get. But makes sense when x is reasonable. So by doing so, I suggest that triangles will tend, of course, depending on the polygon, but I'll try to get the triangulation that the areas of all the triangles are the same. But the same algorithm would work fine with a lot of other cost functions. You'll see in a moment, once I'll describe the algorithm, what makes sense and what doesn't. What I can put it. Okay, yeah.
Quick question. Is it the characteristic of having a small triangle with similar size have any practical application? Or we can just
It will put some pressure against thin slivers. It will, excellent question. Why? I'm not making it into a computational geometry class, but it definitely makes sense that if I think about here is my polygons that I already triangulated in this way, where I have a huge triangle and a tiny triangle, and you can argue that for a lot of applications, this will be a better triangulation than this, because all the angles here are smaller than the angles here. They are more or less of the same size. There is not the thin, very tiny angles of the triangulation are universally hated. They are bad for numerical analysis, bad for strength analysis. Any system that will use these triangles to simulate any physical process will be bad when you render them. What happens when you render them? Okay, since we get to this part. So it's something that I showed in computational geometry, but let's talk about this problem for a second. I measured elevation above sea level. So the numbers that I write through these 4 sample points are elevation above sea level. And these 4 points, just for real estate, here, A, B, C, D. The distance between A and B is tiny. Distance between D and C is huge. The elevation here and here will be 100 feet above sea level, and at C and D is 0 meters above sea level. Now, I need to guesstimate, just based on these 4 points, what is elevation these are measurements of the mountains, terrains, and I need to guesstimate here what the terrain looks like based on these 4 points, which very much depends on how do I triangulate it. Right. Our first assumption would be that between the 0 here and the 100, I'll move linearly. The same goes here, the same goes here, the same goes here. But now let's consider the 2 possible triangulations that I can generate here. If I'll take these triangles, and how is my mountain ridge looks like? Here is a ridge of elevation of 100, and the mountains themselves meet nicely with a very, very modest gradient starting from 0 all the way to this ridge of an elevation of 100. So that would be my preferred triangulation in this case. As opposed to it, what happens if I'll triangulate it in this way? And again, inside every triangle, I'll do just linear interpolation of the 3 relevant vertices. So if this is my triangulation, then this is 0, and now I have very sharp canyon that is going over here between the 100 and the 100. This is 0, this is 0, so along it, it's always 0. While here I have two mountains that sticks out. It's not unconceivable, but these points are very close, so this will be an example of bad triangulation, because at least if I don't have any other data, maybe the first one makes more sense. But it's a bit more in the makes sense. Guys, you understand what we're saying? Yeah, that there are two ways to linearly interpolate between these 2 points, depending on where I put the diagonal. And having a very thin angles suggests that inside a very thin triangle there are extremely rapid changes, while the changes, if I take the other triangle, are more modest. It means that processes here will be more reliable, versus if I'm trying to put heat on this piece of metal, and I'm asking how well can I interpolate everything inside the same triangle. Anyhow, so just about why triangles with large angles are good and why I prefer to have them not changing dramatically in their size. But it's a lot of application domains, with just that much that I can say that is universally true. Anyhow, from now on we have a clean abstract problems. You're given a convex polygon. Again, convex just because I don't want to say each time I check if the edge exists or not. It doesn't really limit. And I want to find the polygon with the smallest triangle, with the smallest cost function. And the cost is sum of squares of the triangles. There's plenty of other cost functions that I could have used. Notations, a bit confusing. So when we use polygonal paths, I counted from 1 to n. Now I'll count it from 0 to n minus 1. So the vertices of the polygon will be P0, P2, dot, 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 all the way to P7. That's polygon with 8 vertices. And I am going to speak a lot about runs of vertices, like one of 2 vertices, one of 3 vertices, one of 4. Notation, always going counterclockwise. I need an arrow because otherwise I'll keep confusing between them. So I always go counterclockwise. And when I'll speak about a run of k vertices starting at some vertex pi, mean I'll stand at pi, go to the next vertex pi plus 1, pi plus 2, all the way up to pi plus k minus 1, if it's only k vertices. That will be the last one. And in terms of indices, it's very clear when I'm talking about a circle, I'm just doing everything here modulo n, modulo number of vertices. So if I start this animation that is completely useless, if I look at one of 4 vertices, then if I start at P3, it will include P4, P5, P6. And if I start at P7, or 4 vertices, it will be P7, P8, modulo 8, making it P0, P1, and P2. P2 is P7 plus 3, modulo 8. Okay, makes sense. Don't be intimidated by the module. Obviously, just going in a circle, this arithmetic. So you wouldn't use the notation of modulo from now on. Next. I will solve sub-problems of the polygon. I'll solve sub-polygon problems. That is, to triangulate sub-polygons out of. So to tell you what are the sub-problems that I specify, I'll just give you 2 indices, I and j. And counterclockwise, you'll think about all the vertices that starts at pi and ends at pj. Counterclockwise. So again, if I tell you P4 to P10, you'll think about a sub-polygon that consists of these vertices. Oops, and once I tell you that P4 P10 is a subpolygon, I'll also tell you that part of my triangulation is to take the chord that connects P4 to P10. Again, if I think about a subproblem P4 to P10, you're thinking about a completely new polygon, which is part of the original polygon. What is this? It consists of P4, P5, P6, P7, all the way to P10 that you need to triangulate. But what's the boundary of this polygon? Well, I'll assume some oracle, if that's a subproblem that I insist of, it means some oracle told me P10 and P4 is a chord of the optimum triangulation. Now, is the oracle right necessarily that this is a chord of the optimum triangulation? Absolutely not. I don't know if that's correct. But when I solve this subproblem, I assume that it is correct and it is called part of the chord. And that's highlight. It's very abstract so far, but it already highlights a very important property of dynamic programming, which is, let's think about the LCS, and let's assume that in the LCS, I don't know all the tricks about suffix, prefix. You're given the LCS problem A, B, C, U, V, W, A, X, Y, Z, and something, 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 A, something, something, something. And there is an element of divide and conquer that we are using very heavily. What do I mean? I don't know if this A is in the matching of the LCS. I don't know if this A participates in the matching of the LCS, and if it does, I don't know to which character it is matched to. But the moment that I take the gamble that this A matches this A, then I split the problem into two subproblems. From now on, remember, chords cannot cross each other, implying that the subproblem of everything to the left finds the best matching, and everything to the right finds the best matching. But if these two A's match to each other, then nothing on the left interacts with anything on the right. It's divide and conquer. And the ways that we solve the LCS just take clever indices of this principle. We are using this divide and conquer idea more strongly in this subproblem. I told you solve the problem of the subpolygon from P4 to P10. So I assume that there is a chord from P4 to P10, and you still have to triangulate everything that is counterclockwise along it. But it also means, since there is a chord P4 to P10, it also implies there is no chord from P7 to P1, because they will interact. It will cross this already existing chord, and chords in triangulation can interact. So what did I do? I broke the polygon into two sub-polygons that each one should be optimally solved. And the cut and paste lemma would say, if you did indeed took the right chord, then what would be the optimum solution? It will consist of the optimum solution to the left and the optimum solution from the right. So now when we have all these ideals, we just need to arrange the algorithm to take advantage of all of them. Okay, so definitions. Everybody understand what is a run of k vertices starting at pi. First definition, Cij, it will be also an entry of my array. Cij is a cost of the optimum triangulation of the sub-polygon that starts at pi and counterclockwise and at pj. So C410 will have, when I'm done, the optimal cost of triangulating the subpolygons bounded by the chord P4 to P10. Okay? That's what the cost is. How would I name the solution to the other half of the polygon? C10, 4 will refer counterclockwise to the other side of the half polygons. Okay, so that's what is Cij. Okay, so when the oracle tells me solve the problem C4, compute for me what is C410, the oracle also told me that the chord P4, P10 is part of the triangulation. And possibly the oracle is wrong, so I'll have to check a lot of such pairs. Okay, let's go back to what are the pi values a bit later, because we'll also need, similar to Dijkstra, we'll need some way to backtrack our method. So let's wait with what is a pi, let's concentrate on the C. So, once again, C410 will be, look at the subpolygon, find a triangulation that minimizes sum of squares of triangles of only this part. Okay, so let's start to initialize the algorithm. Now, what will not work here is to do our standard loop of for I goes from 1 to n, from j goes from 1 to n. Things will not work here. I need a different idea. And the new idea would be, as usual, I want to solve larger problem using solutions to smaller problems. Common here, common to all dynamic problems. What would be the smaller versus larger? What makes it larger? It means that there are more vertices in the problem. The run is longer. So my plan would be handle all the runs of length 0. Once you're done, handle all the runs of length 1. Or subpolygons of 2 vertices, or subpolygon of 3 vertices, then or subpolygon of 4 vertices, always consecutive, always one after the other along the boundary, and so on. And as you increase the runs, eventually you'll get to cover the whole polygon. So let's talk about the init. Again, we go back to the pi. Let's go to the init. For every I and j, unless I know everything else, the best triangulation that I know so far is infinity. As usual, when I look for the minimum, I'll initialize every value to be infinity. And what is CII? How do I triangulate a polygon that consists of a single vertex? It doesn't take much area. It takes 0 square feet. CII is initialized to be 0. What is C of I plus 1? These are runs of length 1. These were runs of length 0. These are runs of length 1. How do I triangulate a single edge? Again, takes 0 out. I need it because you'll see that I do need these values later on. So I still need to initialize it. The only part that I start to fill the geometry is now I'm looking at all the runs of length 3. All the runs of 3 consecutive vertices. That is C of I, comma, I plus 2. It covers the vertex Pi, Pi plus 1, and Pi plus 2. Runs of length 3. Where do you see such a run? Like here, start at P11, goes to the next and goes to the next, as usual counterclockwise. What should C of 11,1 contain? Well, I need to triangulate a triangle, not a lot of options right here. So what I write at C of 11,1, it's 11 plus 2 modulo 12 would be what? The area of the only triangles that you can generate right here. The area of the triangle Pi, Pi plus 1, Pi plus 2, area squared, because that's a cost. I'll look at this triangle, and I'll compute its square volume. So I'll do it for delta 1, that is, this is C of 1, comma 1, C of 11, comma 1, C of 11, comma 1. Don't confuse with C of 1, comma 11. 1, comma 11 is this part. We still don't know how to do it. And similarly, CO4, 6. Look at delta 2, compute its area, square. That's what you write over there. Everybody is good with runs of length 3? Now, it doesn't show in the figure, but of course these triangles happily overlap. But it's not that I go to 3 vertices and the next 3 and the next 3. I check, like the next vertex after 4, 5, 6 would be 5, 6, 7. Makes sense. Triangles overlap. Okay, I think that it said runs of length 2, I should correct it. Here's the main algorithm after the init. I am already done with every run of length 3. C already have all these solutions, and as usual, I play with the cost, not with the actual triangulation, because negotiate triangulation takes a lot of information. Cost is only a number that I need to negotiate about. I don't know, in my other course in 437, I brought a monster to the midterm, and it was extremely popular. I don't know. Yeah. So you can change your mind if you. Oh, and it's your color, for good or for bad. Okay, runs of length 4 now. K, the main variable here, determines the length of the run. I'll start with all the runs of length 4, then all the runs of length 5, all the runs of length 6, and so on. So, let me highlight this P4, P11, and out of all the vertices between 4 and 11, P5 all the way to P10, well, solving the problem from 4 to 10, I need to assume that there will be a chord between 4 and 10, just as before. So I only solve the problem of triangulate everything to the left of this chord. Pi, Pj participates. And what do I know right now? I know the length of the run, that's k. Now, I will be the variable that runs through the start of the run. I'll start the run of length 4 at P0, then at P1, then at P2, and so on. To make my indices a bit simpler, I'll say J is just k steps ahead. It's not a loop on J. J will just be k steps ahead. Okay, I'll take I, that is a loop, add to it k minus 1, that just tells me what is the length of the loop. Right. In the previous slide, if I look at P4, then and k equal 4, then J will be P7. And when I will be P5, then J will be 4 steps ahead. Okay, so no loop about J. But there is a loop here about T. Let's think about T. So what's going on? I just told you that for the time being, PIPJ is part of the optimum triangulation of this part. Meaning that if I stand on this edge and just moving a bit to the left, I am inside one of the triangles of the triangulation. But move a bit to the left from this edge, you're inside one of the triangles. Triangle has 3 vertices. Where is the 3rd vertex of this triangle? I don't know. Which of all the vertices along the run is the 3rd vertex of this triangle? Possibly the next vertex of this triangle would be P5, and then I'll have P4 and P5 connected. and P5 connected. This is an edge of both polygons, and this is one option. Another option would be, here is again P4, P11, Pi, Pj, and whom should it be? P7 will be the other location of this vertex. I don't know where this other vertex is, so I'm just checking all options. T here is the loop. I'll check all the T's that go through what? P5, P6, P7, P8, P9. And here is a divide and conquer. Here is where I'm using the sub-problems, the smaller problems that are already solved. Let's assume for a moment that the third vertex of this triangle is at P7. What is the cost of my overall triangulation of this sub-polygon, the problem of 4 to 10? You need to pay for these triangles of 4, 7, 10. No matter what, you have to pay for this area. If that's where the third triangle is, you're paying for this triangle. Now, remember the cut and paste lemma? If I could have gone to this place in a shorter way, I would use it for the larger problem. The same goes here. How do I triangulate this whole thing? I still need to triangulate the two Cayenne subpolygons. But for the two Cayenne subpolygons, you already know the solution. It's stored in the memory. It's shorter runs, obviously. It's a run now of length k, meaning that all the runs of length strictly less than k, 1, 2, 3, all the way up to less than k, are already solved. So I know what is the cost of triangulating this Cayenne subpolygon. I know what is the cost of triangulating this Cayenne subpolygon. Notice these two Cayenne subpolygon might be just a single edge. That's fine. They don't really exist. It's one of the solutions, it's still less than like what you see on the whiteboard. Make sense? So let's see. For all the T's, all the vertices in between P4 and P7, look at the area, assume that the third vertex is at, assume that the third vertex is at PT. Third vertex of this main brown triangle that I'm discussing all the time is at PT. What are you paying for? You're paying for the area of this brown triangle square plus the cost of the subpolygon from I all the way up to T, up to 7, the first Cayenne subpolygon, again it could be just an edge, plus the area from triangulating all the subpolygon from PT all the way to PJ, the end vertex. Compute this cost, and now I just check, is this better than any other of the subpolygons that I kept by moving the third vertex along it? That is, all this part is doing is find the minimum when you're checking this third vertex all the way around. Cool? And that's it. And that's how I'm getting rid of all the runs of length t, and I'm ready to move to runs of length t plus 1. And eventually what I'll get at the end is runs of length n, which are just the whole polygon. So it's clever and different way to address pies, to address memorization. By the way, CLRS doesn't contain this example, but if you're completely lost, it's similar to the matrix multiplication that CLRS does contain, that is slightly similar in flavor. Okay, let's talk about what are the pies. What is the purpose of the capital pies over there? When I filled the Frechet edit distance dynamic time warping yada yada, all I need to care is who influenced this cell, either the cells to the left or above, or diagonal or above. One of these cells we are the only candidates, and it was easily to check from this, looking at that this cell contains some value 17, I can easily check based on the input which of these cells correspond to. Now, if I want to reconstruct the actual triangulation, it's a bit tricky. I don't want to do the search ahead of time. What is the information that I need to have together with Cij? If I know already what is Cij, what is this area, smallest area that I get, I know, since it's an Ij problem, I know that Ij is an edge of this triangulation. What it's not obvious to me is where is the third vertex that gives me this optimum value. I need to memorize it. And for every pair Ij, ordered pair Ij, from I to j counterclockwise, I need to say, remember who is the third vertex that gave you the best solution so far. Okay. You have the homeworks to actually play a bit more with the reconstruction, but let's look back at the previous slide about how did I initialize it already. So when I talked about the case of ones of 3, that is single triangle, P11, P11, P0, P1, I had to say that C of 11 to 1, C11 to 1 contains the area of this triangle. Where is the third vertex of this triangle? It's, well, not much choice. It will be at Pi plus 1. That is, it will be P0 in this case. In general, if you remember the values of pi when you run Dijkstra, when I run Dijkstra and I find the way from me to Phoenix, what Phoenix needs to know is not the whole path to Phoenix. It just needs to know what was the last step of the path. And then I can go back one path and ask, hey, for one vertex before that, what is your pi? If you are along the shortest path, who was before you? Go to this guy who was before you. So we find the path from Tucson to Phoenix forward by propagating cost, but we reconstruct the path always backward. Same for the Frechet's eddy distance. We first fill the matrix, and then we find our way upward in the matrix. The same you're doing with pi. Everybody's good? Okay. Now, out of all the dynamic programming, that's solution that this problem works as magic. It's like the solution, maybe in a negative way. It's really surprising that it works. So clustering, surprise, surprise, is NP-hard. Any type of clustering of points by, say, I want to place centers, and I want to assign for every center a group of points, so that all these points are close to the center, and I don't want to use more than 17 clusters. Classical problems, it's all NP-hard. You know, there are algorithms that can approximate it. There are lots of fantastic heuristics, but exact solution is hard to find. On the other hand, here is an example where it will be much easier. And polynomial. Oh, I forgot. What was the running time of the triangulation algorithm? Not much to negotiate, right? It was, go back, running time after it was, I ran with the starting point, that was I. Now, for the same starting point, so, sorry, I run with all the length of the run, that's n. For now, I start from where is the starting point, another n, and now between the start of the run and the end of the run, I need to check all the t's are the location of the third vertex, another n. So n cube. And at the top of my head, I don't know if there is any way to get linear memory. How much memory do I need without any tweaks? It's n cube time, but memory is n squared for all the ij, just what's the cost. Again, that's why I don't want to negotiate or to propagate description of the whole triangulation, just the cost of the triangulation. Okay, Here is clustering that actually works very nicely. But its caveat, it's not a big problem. But so I want to break a set of points. Let's jump one slide. I have a set of points. They are coming without colors. So all these points come without colors. They have some time domain that appears here. So I got the value of my stock at different locations, some other process. And what I'm trying to say is that there is a lot of error noise when I measure the location of the points, but all in all I want to say there is some period where things behave kind of linearly, going downward, then the market change, it starts to go upward. I also color these points differently. Then something else happens and I can cluster them in a different location and so on. So I have time sequence of points and I want to break them into meaningful clusters. So to start, what would be a cluster? It would mean that I can, a necessary, not sufficient condition of subset of the points to be a cluster would be that they all exhibit somehow the same behavior. For simplicity, I say the same behavior, meaning approximate by a straight line. But you can replace this criteria by any other criteria that will say there is a good group among this set of points. So approximate by the same line will be a good example. And the big difference between this problem versus clustering in 2 or more dimensions would be that now when I cluster my points, again, they are coming without colors. It's up to me to decide what belongs to each cluster. What I decided is that since it's time domain, when I specify a cluster, I specify a period of time. Where does it start, where does it end? And if I try this hypothesis, then every point between the start and the end of the cluster must belong to the same cluster. That's what makes it much simpler than clustering in 2 dimensions. Make sense? I told you when a cluster, a period, an era starts, where does it end? Everything in between must belong to the same cluster. But it's up to me to decide when a period starts, when a period ends. Okay, back to our problem. How do I approximate set of points? How do I define if they are more or less linear? I picked a norm that most of you know. If I have a line specified as ax plus b, y equal ax plus b, say this line, I can define the sum of squares error, different names, defined as follows. Look at each one of the points with respect to this fixed line that you have. Look at each one of the points. Think about xi. Tell me where the point xi on the line that I told you. Look at the data points p4 over here. I can compute this point, I can compute this point, I can ask what is the vertical distance between them. It's one above the other vertically. I can ask what is the vertical distance between them. Take this distance and square it, just as before. And do it for this point and this point and this point. And this point, look at the sum of square of all this vertical distance to all the points xi, yi. Xi, yi are points in my set of points. So right now I have one cluster. I just asked how to approximate it. Hopefully many of you have seen it before. Where is it going from here? Now I want to find the line that fits it best, very practically, in statistics. How do I do it? I look at this expression, sum of ax plus b plus y squared. Remember, the points are given to me. I don't have any control about them. What I need to decide is what's the best line. So one of the reasons that I wanted to square it rather than to sum up, say, the absolute value, is that it's differentiable. It's continuous and L1. It has continuous derivatives. So this expression is just a function of two parameters that I need to decide about. What is A, the slope, and what is B, moving the line up and down. So I can look at this expression, take the partial derivative by A of this expression, and say if I just hit the right A, then the partial derivative must be 0. But how do I know that A parabola reached its optimum, maximum or minimum? I look at the derivative, see how the derivative changed, and if I hit the minimum, it means that the derivative is 0, because it means that there is no direction, neither left nor right, that will improve my cost function. Okay? Takes a partial derivative. Just out of curiosity, how many of you have seen this symbol before? Partial derivative. Most of everybody. You're good with partial derivative, derived by A, derived by B, compared to 0. Now everything else sums up. You have a small formula that tells you what is the optimum A, what is the optimum B. Easy problem, just linear equation with two linear equations with two variables A and B. Notations. From now on, when I'm talking about the error of a line L given L, fixed A with A and B, and the error with respect to a set of points S, this is the expression that I'm talking about. But when I use the same notation, error of just S, and I omit the L over here, they understand it as it's the error with respect to the best line that you can fit for this set of points. Okay? When I write error without L specified, means L is found and it's the best line for this set of points. Now, given this set of points, compute the best line takes linear time. That's easy, just sum up all these expressions. What is not hard to say is that if I'll add one more point to S, then I'm spending a constant time on all this expression. I'll update the errors that are also simple expression. Adding one more point takes a constant time. Adding one more point takes a constant time. I don't show you the details, they're boring. But in general, if you give me all the pairs of values, I and j, I smaller than j, and I want to ask what is the error that best fits the set of points that starts at pi all the way to pj. Again, once I told you what is I and j, I must include all the points in between. Pi plus 1, dot, 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 pj. What is the error of all the way from pi to pj? That will take order n squared. So far, nothing complicated. Just by fix I and then change j to be I plus 1, I plus 2, I plus 3, and as we said, add one point will take a constant time. Okay, so once again, error from I to j, just a shorthand of the error from pi to pj. And again, you could have used quadratic, you could have used other functions to fit, I don't care. It's still a framework that will work. So now, after all this big introduction, what is the overall problem? I want to describe about what is the main clusters over here, but it's a really ill-defined question. What are the clusters over here? I have no idea. I want to find clusters that minimizes the total error with respect to each one of them. But at the same time, if I can find fantastic clusters, like take the first 2 points and approximate them by a line. Take the next 2 points, approximate them by a line. Every 2 points is a cluster. No error at all, but a lot of clusters. Or I can decide, insist on one cluster and live with the results. So the way that I control it will be, one way is to say I have a target number of clusters, which is one way to control it. Another way to control it is to say, let's decide that every time that we are adding a cluster, there is some penalty involved in it. Now, the penalty is not something that we calculate. The penalty is something that the user can fine-tune. The user can change what is a penalty, and as you change the penalty, the number of clusters will change. But the way that we are inputting the penalty in the game is every time that a new cluster is open, starting from the first one, every new cluster will cause this penalty. Now, if the penalty is huge, then you don't want more than one cluster. Because no matter what the numerical error, you will not, it will not balance. If the penalty is zero, close to zero, every pair of points will be a cluster, because then you can afford many clusters. In general, the larger the penalty is R over here, I don't know why, but that's what the book picked. R will be the penalty. For each cluster, I'll add this penalty, and what is the overall cost that I'm trying to find? What I'm trying to find is clusters, start at P1, goes to some other point, P5. Start at the next point, P6, all the way to P8, next cluster, and so on. And what will be the overall cost, the total cost that we are paying for the whole set, is defined by the penalty for the first cluster plus the best line that fits the first cluster. I need to, as part of the algorithm, also to tell me where the first cluster ends, where the next cluster starts. Once I know where the first cluster ends, the next cluster will just start at the next point. Sorry for the double indices. So I1 is the number that I need to compute. That would be the last point on the first cluster. That's what the 1 tells me. I1 plus 1 is the next point in the next cluster. I need to compute it all the way to I2 is the index of the last point of this cluster. Pi2 plus 1 is where the next cluster will start, yada yada, all the way until the last point. So I need to decide how to break all these points and what is the cost that I'm paying. For every cluster, find the best line, find the error with the best line for this cluster, of course. Find the error, the sum of squares of this vertical arrow. Take the error of the first cluster plus the penalty, plus take the error for the second cluster plus the penalty for opening a new cluster, so on for the last cluster. So just to show you how it works. So here I have two clusters. Asking the homework to play actually with this app, and I can change A. A right now on 8. The slider that you cannot read, but the slider that says A tells me where the first cluster ends, and obviously the next cluster will just start at the next point. And if I insist on 2 clusters, then I need to pay penalty of 2 times R, and I need to decide how to move A, that is, so that how to move A, where do I cut from the first cluster to the second cluster, and for every cluster, what is the total penalty, or what is my total cost, this distance square, this distance square, this distance, yada yada, with respect to the best line, plus the same deal for the second cluster, plus 2R, sorry for the font, it said somewhere 2 times the R, the cost that you found. Now, if you are picking R that is large enough, then probably your best policy would be to actually to pick only 1 cluster that covers everything. And then you need to pay only 1 R. Or if the penalty per cluster is small enough, then maybe you want to shoot for 3 clusters. Right? You'll have 3 clusters, again, that you can control by A and B, where this will be the first, second, and third. You have to decide where each one starts. And what is the cost that you're paying here? 3 times the penalty, 3 times R, plus the error with the best line for the first cluster, first error, and first for the. Everybody understand why this awkward cost function actually makes sense, and where is R in the game? I don't control directly the number of clusters. I control how much you're willing to pay for opening a new cluster. Now, why is this dynamic programming? Why we can solve it in dynamic programming? I already mentioned the dynamic programming usually works well with divide and conquer. So where is divide and conquer here? How do I partition the problem into sub-problems? I should have let you think about it, but for the sake of time, where is this becoming sub-problem? Well, let's say that I decided on 3 clusters, and let's say that I told you that this point that you cannot see its index, that's the last, that this point will be the, let me have one try. Slightly better. Okay, it looks, yeah, slightly better. So I just told you that I am going to use 3 clusters, indeed. Did I lose a cluster? Yeah. Yeah, I'm using 3 clusters. And I told you that this point is the beginning of a new cluster. This point is a beginning of a new cluster. It means that previously I have some number of clusters, but how would I cluster and fit lines to all the points that happens to the left of my line? Dijkstra, once again, cut and paste. It's a sub-problem that you want to solve optimally. If this is indeed where a new cluster starts, look at all the points that appeared until this point, you will use the optimum solution for this subset. Now, it doesn't mean that this optimum solution for the point from this point to the left is actually what you'll use, because possibly I want to change the clustering by adding more points to the right. But if the oracle told me a new cluster starts right here, then everything until this point should have the optimum solution to this separate sub-problem, find the optimal solution for the much smaller problem of clustering all the points from 1 all the way to where I told you to cut it. Oh, and we're running out of time. So thanks, everybody. Questions up to this point? I mean, the algorithm is going to look like magic. It took me tons and tons of time to start to make sense. And by the way, it's taken from the book of Hochbaum. Sorry, that's from the book of Kleinberg and Tardosh. That you can, with a bit effort, you can find it more legally or less legally in various places. Okay, thanks everybody.